in absolute value decreases as labor increases. So we can draw one isoquant here and look at what happens to the marginal rate of technical substitution. So I'm going to do 10, 2, 7, 3, 5, 4, 4, 5, 3, 7, 2, 10. Okay, so if I draw my isoquant, had it so nicely done here. That's better. My isoquant for 10 units, on the y-axis I have capital, on the x-axis I have labor. What's the marginal rate of technical substitution? So let's try and figure it out. A, B, C, D, E, F. So I'm going to go from point A to point B. I'm going to figure out how many units of capital I can give up if I add one more unit of labor. So what happens here, as I go from A to B, let's use a different color here. So I go from A to B, if I give up 3 units of capital, I add one more unit of labor. So change in capital is -3. Change in labor is 1. Right? If I give up 3 units of capital, I only have to add one more unit of labor and I produce the same output. Or the other way around, if I add one more unit of labor, I can give up 3 units of capital and produce the same output as before. So here, from A to B, the marginal rate of technical substitution is the change in capital over the change in labor. It's going to be -3 over 1, which is equal to -3. If I go from B to C here, right, I do this 2-step move. I give up a certain amount of capital and I move across by adding one more unit of labor. So the change in capital required here is -2, which I can replace by one more unit of labor. So the marginal rate of technical substitution here is -2. Here, I'm not going to be as explicit as I was with the other ones. If you add one more unit of labor, you give up 1 unit of capital. So the marginal rate of technical substitution is -1. Here, you add 2 units of labor, you get to give up 1 unit of capital. So the marginal rate of technical substitution is -1/2. And here, you add 3 units of labor, you get to give up 1 unit of capital. The marginal rate of technical substitution is -1/3. Right? It's always the change in K over the change in L. So what we're seeing here, as we're going from the top left to the bottom right, we start with a marginal rate of technical substitution that's a large negative number, and we move towards Miami, and it goes from -3 to -2 to -1 to -1/2 to -1/3. It becomes a smaller negative number. So the way economists would say that, and I will always be clear in exams, but if you're confused as to whether I mean a negative number or the absolute value, just raise your hand and we'll say it. We'll say the marginal rate of technical substitution is diminishing along an isoquant. The reason we don't bother with a minus sign here is we realize it's got to be a minus. You give up some capital in order to add more labor, or by adding more labor, you can give up some capital in exchange and still produce the same output. So much, if you go back in your notes and you look at when we looked at the marginal rate of substitution, I drew you the exact same picture, only the labels were different. There was Reese's and Hershey's, and here there was some utility label on there. Now we have capital and labor, which are cardinal quantities, and a cardinal label on the isoquant right here. But same property, marginal rate of substitution is diminishing along the isoquant. So what did we do next? We showed that the marginal rate of technical substitution, which is the change in capital over the change in labor along a given isoquant, is related inversely to the marginal utilities of those two goods. The marginal utility of labor, marginal utility of Hershey's over the marginal utility of Reese's. I'm going to show you now that something very similar is true for the marginal rate of technical substitution, namely that it's going to be inversely related to the marginal products of those two inputs. So let's do it. Can we relate what we know, the marginal product of labor and the marginal product of capital, to the marginal rate of technical substitution? Well, the answer better be yes, right? Because otherwise I'm wasting precious 15 minutes of your time. So what we've got now is time for a proof, right? So before you do a proof, what you need to do is you need to make sure your number 2 pencil is sharpened. So if you're using that, pull out a new pencil. Then you take both of your hands, you take them like this, you turn them around, and you stretch, right? Sit up straight, and you start. So the marginal product of labor was defined as the change in output over the change in labor. Similarly, the marginal product of capital is defined as the change in output due to a change in capital. So the marginal product of labor holds capital constant, the marginal product of capital holds labor constant. So now what I'm going to do is I'm going to do math that requires a supercomputer, okay? I'm going to multiply both sides times delta L. So delta L times MPL equals delta Q. For the other equation, I'm going to multiply both sides by delta K. Delta K times MPK equals delta Q. Now, since the marginal rate of technical substitution is defined for a given isoquant, right? For a given isoquant, an isoquant means same quantity. The change in quantity along a given isoquant is 0, right? Same like the change in utility is 0 along a given indifference curve on an isoquant. So now I have two things that are equal to 0. Two things that are equal to the same thing are equal to each other, all right? Still love that quote. Delta L times MPL equals delta K times MPK. Now what I'm going to do is I'm going to take my delta L and I'm going to bring it over here, and I'm going to take my MPK and I'm going to bring it over here. So I'm going to rewrite this as MPL over MPK is equal to delta K over delta L. That's not a C, that's an L. So I don't have any cash on me, otherwise I'd gladly pay somebody $5. Where's the gentleman I paid $5 to next time? I just want you to confirm in front of the class that I paid up. Did I pay up? I did pay up, right? So I paid my $5. I don't just write IOUs that you can't cash in. So the point here is, now I've got an equation by just acknowledging the fact that I'm on one isoquant here, so changing quantity is 0. I've set this here equal to that, just rearranged it, and I've got marginal product of labor over marginal product of capital is equal to delta K over delta L. The change in K over the change in L is equal to the marginal rate of technical substitution, because that's how we defined it. So the big aha moment that you didn't see coming at all, because I didn't spill enough crumbs to lead Hansel and Gretel all the way to Hawaii, right, is that the marginal rate of technical substitution is equal to MPL over MPK. Hold on, what's my next slide? Okay. So I want to sit with this for a second and compare this to what we had earlier, right? So marginal rate of substitution was equal to the marginal product of marginal utility of Hershey's, the marginal utility of the good on the x-axis, divided by the marginal utility of the good on the y-axis. The marginal rate of technical substitution, which is the slope of the isoquant, is equal to the marginal product of the good on the x-axis over the marginal product of the good on the y-axis. Same thing. So let's build a little bit of intuition for exactly 2.5 minutes and then move on to exciting other topics that you never knew you had to know. If I'm at the very top here at point A, do I have a lot of capital? Yeah. Do I have a little bit of labor? Yes. Right? So what's probably true about the marginal product of capital when I have a lot of it? Is it big or is it small? It's going to be small, right? Because we know the marginal product of capital is diminishing eventually. So it's probably going to be small. So let's just remember the marginal rate of technical substitution is marginal product of labor over marginal product of capital. So up at A, this number is probably small. You have very little labor, right? So what's the marginal product of labor probably like? It's probably pretty big, right? So the second worker you hire adds a huge amount of marginal product because the person all of a sudden stands at the cash register and the other one sells the pastries. So at the top left, MPL is big, MPK is small, right? So this is going to be a big number in absolute value. What about down here? The opposite is true, right? I have a ton of labor, so the marginal product is probably small, and I have very little capital, so the marginal product of capital is probably big. So this here is going to be a small number. So the ability of a firm to substitute between inputs depends on the size of the stash of capital versus labor that they're using and the marginal products that go along with it. So again, in consumer choice, the marginal rate of substitution depended on how big your stash of Reese's relative to that of Hershey's is, and the marginal utility that went along with your big or small stash. Same thing translates here, only now we're talking about cardinal things and marginal products and marginal rates of technical substitution, instead of talking about ordinal things like utilities, the cardinal goods that we're consuming, and the ordinal marginal utilities before. So everything translates very nicely, only now we live in a fully cardinal world here, right? There's nothing touchy-feely utility in producer theory. None of that. Okay. A couple more concepts I have to get to before we get to costs. You're lucky I don't think we're going to get to costs today. I sacrificed that in favor of my Malthusian rant, but that's okay. By the way, if you ever disagree, I don't intend to be preachy at all. I love an argument, all right? I'm that guy. So argue with me, either here or in office hours. Here, I'll probably cut you off. So returns to scale. Returns to scale is a word that people, it's actually not a word, it's 3 words that people throw around a lot. And when you ask people, what do you mean by that? They never know what they mean by that, right? Scale economies are very important for American progress. Yeah, that's probably true, but what do you mean by scale? Oh, I don't know. Okay. So let's define exactly what economists mean when they say returns to scale. Returns to scale, first of all, are a long-run concept, right? Returns to scale live in the long run, they don't live in the short run. So returns to scale mean, how does output change if all inputs are increased by equal proportions? The easiest way to remember this is to just say, what if all inputs double? What happens to output? So constant returns to scale means you double all inputs, you double output. This is your potato salad production function. Potato salad, in the worst of times, has 2 ingredients. Bad starchy potatoes and cheap mayonnaise. Right? Gross. Germany takes its potatoes seriously. But for this production process, that works pretty well. You double the amount of mayonnaise, you double the amount of potatoes, you get twice the potato salad, right? You double all inputs, you exactly double output. A decreasing returns to scale production process, you double all inputs, but you less than double output for some technological reason, and we will talk about why this could happen in a little while, right? But if you double all inputs, right, let's say you're using 100 units of capital, 100 units of labor to produce 100 units of output, you double capital to 200, you double labor to 200, all of a sudden you're only producing 180 units of output, so you less than double your outputs. This is an example of a decreasing returns to scale production process. Increasing returns to scale production processes, they're not unicorns. They actually do exist quite frequently, and we will talk about this when we talk about utilities and energy and all kinds of interesting stuff. But increasing returns to scale are production processes where you double all inputs and you more than double output, right? So if you had 100 each of labor and capital and you produce 100 units of output, now you double labor to 200, you double capital to 200, and all of a sudden you're producing more than 2 times 100, you're producing something like 250 units of output, right? So doubling inputs more than doubles output, that means increasing returns to scale. So does a firm always fall into one of these buckets? Not necessarily, right? A firm's production function can have areas where you have increasing returns to scale for over a certain range of production, then constant returns to scale, and then decreasing returns to scale. Really depends on the technology you're using. I'm going to draw you all 3, and then we're going to go home and start meditating for our exam, okay? Actually, don't meditate, study, okay? Constant returns to scale. What does a constant returns to scale production process look like? It looks something like this. Also a favorite exam question of mine. What you want to do is you want to draw something where you can easily double all inputs. So I usually start with 2, 2, right? Pick the point where I'm using 2 units of capital, 2 units of labor, and I'm going to draw an isoquant through this point. And I'm going to say at this isoquant that goes through the point where you're using 2 units each, you're producing 10 units of output. Now constant returns to scale says doubling all inputs, you exactly double output. So this means if I double labor, I'm at 4. I double capital, I'm also at 4. So the point here now is 4, 4. So let me draw the isoquant, ignore this part here. That shows constant returns to scale. Well, if I doubled all inputs, I have constant returns to scale. The label on this indifference curve has to be 20 units. If I double inputs again to 8, 8, the label on this isoquant right here, now you've gone from 4, 4 to 8, 8, so you have to go from 20 to twice that, so the label here has to be 40. Okay? This is constant returns to scale. Now, I know I'm going fast, but this stuff is easy. Decreasing returns to scale. If you started at 10 units with 2, 2, now if you double all inputs, you go to 4, 4. You draw your isoquant through here. But now, doubling your inputs, less than doubled output. So any number here would work that's greater than 10 but less than 20. So I'm going to pick the number 19 because that's today's date and my sister's 30th birthday. Happy birthday. She's way cooler than I am. Okay, because it's not very hard either. But the point here is now if I double inputs again from 4, 4 to 8, 8, the label on that isoquant has to be less than 38 and greater than 19. So let's pick 35 because that's a great number. So it's decreasing returns to scale. For increasing returns to scale, you would just go from 10. Instead of having 19, you would have a number greater than 20. Right? So let's pick 25. And if you doubled inputs again, the output would have to be more than 2 times 25, would have to be more than 50. Right? So it just means doubling inputs, what happens to output. Number one way to screw this picture up on your exam, people are so focused on getting the 2, 2, 4, 4, and 8 right and drawing the isoquants, and they forget to put labels on the isoquants. If you don't label the isoquants, I don't know what returns to scale you're telling me. Right? So you have to label your isoquants on the exam. Now my last word for today is going to be varying returns to scale. So what does a production process look like? Lars? Yes, yes. So varying returns to scale are pretty cool. The picture would look like this. I'm going to start at 1, 1, then I'm going to double my inputs to 2, 2. Then I'm going to double them again to 4, 4. And then I'm going to double them again to 8, 8. So I'm going to draw, no, that's terrible, 3 isoquants. Okay, so if your first isoquant, you start at 10. Let's draw increasing returns to scale first. You double inputs, you more than double output. So you start at 10. In order to have increasing returns to scale initially, 2 times 10 is 20. So pick a number that's bigger than 20. 25 is an awesome number. Then I want to draw a range where the firm has constant returns to scale. So I've doubled inputs again from 2, 2 to 4, 4. I start at 25. To get constant returns to scale, I double inputs, I exactly double output. So quantity here has to be here exactly 50. And then I want to draw a range where this firm exhibits decreasing returns to scale. So I've doubled inputs again from 4, 4 to 8, 8. So I'm going to less than double my output from 50. So how about, I don't know, 78. Okay, so the take-home message here is one where returns to scale are a long-run concept that deal with increasing inputs by equal proportions. Doubling is a good way to think about it. And then there's 3 flavors, constant, decreasing, and increasing. And each firm doesn't just have to have one of these, but the same firm could have portions of production where at low levels of output you have increasing, slightly higher levels of output you have constant, and then you have decreasing returns to scale. Next time we'll do technological. Now next time we'll do an exam. The time thereafter we're going to do short-run costs and all kinds of other fun stuff. Have a nice weekend, and I will see you tomorrow from 2 to 3:30 at the review session.